Hello everyone, welcome back. My name is Mr. Cobalt, and in this video I'm going to talk about VSEPR theory, and I'm going to talk about the effects of lone pairs and the use of VSEPR theory to talk about the distinction between uh, the electron geometry and the molecular geometry. And the key differences between the two is that the electron geometry takes into consideration all electron groups, so bonding and non-bonding electron groups. And the non-bonding groups are your lone pairs. So you count all of the bonds and all of the lone pairs around your central atom, and then based on that number, whatever that total number is, that gives you the electron geometry. However, the molecular geometry is focused only on the bonded atoms. So what does the bonded atoms look like? So basically this is getting at the actual molecular shape, not the shape with including the lone pairs, but only the shape of the molecule itself, ignoring those lone pairs. So what does the atoms look like arranged in space around that central atom? And that's what your molecular geometry is looking at. So there you do have to take in consideration the number of lone pairs you have on your central atom, and that will determine your molecular shape as opposed to the electron geometry. So molecular geometry versus electron group geometry or electron geometry. So whenever you have lone pairs, this is going to make a distinction between the two. If there are no lone pairs on your central atom, then the molecular geometry and the electron geometry are identical to each other. So in those cases, there's no distinction between the two. But as soon as you throw lone pairs onto your central atom, now the two are going to be distinct. So your electron geometry will be different from your molecular geometry. And in addition to that, as soon as you throw lone pairs into your central atom, you will not have ideal angles. Because again, the lone pairs are going to take up more space. They're going to be they're going to have more of a repulsive force on the other electron groups, therefore pushing them more away and towards each other. So that's going to change the bond angles. So you're not going to have ideal bond angles. So in this video, I just want to kind of go over the basics. In another video, I'm going to use a PowerPoint where I can actually show you pictures of what this looks like rather than me trying to draw them on the board. It's a lot easier to just refer to the pictures of the molecules when we're talking about the molecular geometry versus the electron geometry. But I do have a few examples to help highlight the differences a little bit. So we're going to start with three electron groups, atoms or molecules where the central atom has three electron groups around it, and maybe one or two of those electron groups are going to be lone pairs. So the example I want to use is SO2. So if you draw the Lewis dot structure for SO2, it looks like this. So you've got your two oxygens bonded to your sulfur. Sulfur has a lone pair. And so and then remember, this double bond, don't be fooled by the double bond being there. There is resonance here. So there will be an average of 1.5 bonds between the two. So these are equal bonds, which means that these are equal in their effect on the repulsion. So now, if we're looking at the electron geometry, I count every group, including lone pairs. So here I have 1, 2, and 3. So the total number of electron groups is 3. So therefore, the electron geometry is going to be trigonal planar. So that's what the electron geometry is according to the total number of electron groups. When you're talking about molecular geometry, you're only looking at the bonding groups. So I have 1, 2 bonding groups, but I have 1 lone pair. So if you think about the molecular shape or molecular geometry being about the atoms, not the lone pairs. So you cover up the lone pairs and you look at that and it's a bent shape. So the molecular geometry is going to be called bent, right? Because you got this bend in the molecule. Why is that bend there? Because you've got lone pairs here that are forcing the bonds closer to each other. So if we're looking at the 3 lone pairs, so if I draw this, here I have my lone pair, you'll see the trigonal planar electron geometry. But if we ignore the lone pair and we just look at what the molecule looks like, then that's going to be a bent molecular geometry. So the molecule is bent, but the electron group geometry is trigonal planar. Okay, so that is a clear distinction between the two, and hopefully that clarifies what I'm referring to when I talk about electron group geometry versus molecular geometry. Molecular geometry, I'm only looking at the atoms. How are the atoms arranged with respect to each other? So you can see the bend, and so therefore the molecule is bent. So molecular geometry bent, electron group geometry, or just electron geometry is going to be trigonal planar. Okay, so that's when you have 3 groups. What about 4 groups? So I have 2 examples using ammonium and water. So if you have carbon methane, right? If we add methane, let me just draw methane really quick. So I have H, H, H. So before we said, okay, if you have 4 total groups around your central atom, that then you're going to have an electron geometry of tetrahedral. So here I have 4 atoms, no lone pairs. The total number is 4. So the electron geometry is tetrahedral. But because there's no lone pairs here, the molecular geometry is also tetrahedral because the atoms are connected in a tetrahedral fashion. So I have atoms, I have bonds and atoms, 4 of them, no lone pairs. So it takes that tetrahedral shape. So the actual shape of this molecule is tetrahedral because the atoms are all placed in a tetrahedral fashion. So here I have ammonium and water. You'll see ammonium has 4 total electron groups. I have a lone pair 1, and I have 3 bonding groups. So I have a total of 4 groups. So once again, because you have a total number of electron groups, bonding and non-bonding, the electron group geometry is going to be tetrahedral. So the electron geometry is tetrahedral here, just like it's tetrahedral here. The only difference between this and this is I have a lone pair instead of a bonded atom. But again, the electron group geometry, the electron geometry only depends on the total number of groups, whether or not they're bonding or non-bonding. Okay, so same thing with water. I have 2 bonding groups and I have 2 non-bonding groups, so I have a total of 4. So the electron geometry here is still tetrahedral. So this is tetrahedral electron geometry, this is tetrahedral electron geometry, and this is tetrahedral electron geometry. Now what about their molecular geometries, right? Their molecular shapes. Well, if you look at this shape here, that's tetrahedral as we said, but what if this was a lone pair? So if I cover that up, look at the shape of the molecule now. That does not look the same as tetrahedral. That looks different from that. So if you look at ammonium, this lone pair is not an atom. So when we're looking at the shape of the molecule, we're only looking at the atoms. So if you cover this up and just look at that shape, that's a different shape. That's not tetrahedral. We call this Trigonal Pyramidal. So trigonal pyramidal is what it's called, because you can see a triangular base between these. So you have a triangular base, right? So you have a triangular base, and then the nitrogen here is the top of the pyramid. So it's trigonal pyramidal. So the molecular shape here is trigonal pyramidal, or the molecular geometry. The electron geometry is still tetrahedral, just like your methane. So this is tetrahedral electron geometry. This is tetrahedral electron geometry. The molecular geometry for methane is, again, tetrahedral. However, the molecular geometry for ammonia is not tetrahedral. It is trigonal pyramidal. Now, what about water? Water has two lone pairs. So if I had these two, if these two were lone pairs, I would cover them up and ignore them. What shape does that look like for the molecule? So the molecular shape, look. If I cover this up, look at that. What do we call this? Bent. If I cover this up, what do we call that? Bent. So if I have two bonding groups and two lone pairs, then I get a bent molecular shape, a bent molecular geometry, because again, I'm ignoring the lone pairs. Okay? So if I want the electron group geometry or electron geometry, then I'm not ignoring the lone pairs. So the two lone pairs here plus those two bonds are four groups. So four groups means tetrahedral electron geometry. But for the molecular geometry, I'm ignoring the lone pairs. And the lone pairs are still there, but look at the shape of the molecule. Why are these here? It's because the lone pairs are pushing them closer together. So I'm not changing the shape of this. I'm just ignoring that and just looking at how it looks here. So that is bent. So in this case, the molecule has a molecular shape or molecular geometry of bent, but has an electron group geometry or just electron geometry of tetrahedral. So as you can see, the electron geometry and the molecular geometry is going to be different if you've got lone pairs. If you don't have lone pairs, then the electron geometry and the group geometry are identical to each other. There's no difference between them. And then you can see here with 5 electron groups, you got electron group here. When we have 5 electron groups total, we have 4 bonding and 1 lone pair. Again, if you have 5 electron groups total, right, bonding and non-bonding, we said that was going to be trigonal bipyramidal, right? So this has a trigonal bipyramidal electron geometry. But because it's got lone pairs there, the molecular geometry is going to be different. And in my other video, I'm going to cover that using a PowerPoint so I can use pictures to show you what's going on. I hope you enjoyed this video. I hope this was helpful in clarifying the distinction between what a molecular geometry is versus your electron geometry. The other thing I want to point out again is whenever you throw in the lone pairs, that's going to affect your bond angles. So if you have lone pairs in your molecule, the bond angles will not be ideal. So here we said the ideal angle was 120. But since we have a lone pair here, the bond angle here is not going to be 120. They're going to be pushed more closer together. So this is actually going to be less than 120. Right? So this angle is less than 120 because of the lone pairs. The lone pairs are taking up more space. Here, we said the bond angle is 109.5 degrees. That's ideal. But when you throw lone pairs in there, that takes up more space. They're going to be pushing more. They're going to be repelling more. So these guys are going to be closer together. So we would expect that the bond angle would be less than 109. Oops. So less than 109.5. So actually it's probably 107.5. Right, or 107. So here it's going to be less than, so it's going to be like 104.5 or something like that. In the next video, I will discuss